Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a pre-calculus lecture. I hope you enjoy it. This is the beginning of chapter 4, which is on trigonometry, right? And 4.1 is on radian and degree measure. All right. So in here, with radian and degree measure, we're talking about angles. All right. So let's talk about what an angle is. An angle is, well, we're going to take a ray, this being a ray, and then we're going to take a second ray and join them together at their beginning points there. This first ray here, this is called the initial side. The angle is measured out this way, and we're going to call that angle theta. And this over here is called the terminal side. All right. The point at which they meet is called the vertex. And theta here, this, when we measure this, that is the angle itself. All right. Now, that's angles in general. Let's look at angles in standard precision. When we say an angle in standard precision, what we're saying is we're going to put that angle on the coordinate axis. All right. And in here, we always start by putting our vertex at the origin, our initial side on the positive x-axis, and our terminal side elsewhere. All right. So for example, we can have this angle. All right. And this measurement right here, that theta, is our angle. All right. Where this is our initial side and this over here is our terminal side. All right. And again, it doesn't necessarily have to end here in the first quadrant. In fact, let me just quickly show another possibility here for an angle. We can say it starts here. Remember our vertex at the origin, our initial side over here. And we can say, well, for example, we've got this angle, theta. All right. Now, in both of these cases, our angle theta is a positive angle. It is greater than 0. All right. The reason for that is because from our initial side, we are going counterclockwise. All right. So counterclockwise denotes a positive angle. Similarly, if I said, well, let's start our angle. Well, we have our initial side right there on the positive x-axis, our vertex. Now, we can talk about negative angles if we measure clockwise. So here, this theta, this angle, is less than 0. All right. And again, it doesn't necessarily here need to end at that quadrant. So we would have something like this. Again, our vertex at the origin, our initial side on the positive x-axis, and we can say this right here would be our theta. And again, that theta would be less than 0 because we're measuring clockwise. So measuring clockwise gives us negative angles. Measuring counterclockwise gives us positive angles. All right. Now, noticing here that I've called all these angles theta in general. So I'll make a note down here. In general, angles are denoted with Greek letters. All right. So the most common one you'll be seeing me use is theta. Sometimes I also use phi or alpha or beta. All right, I will be using these in general, but most likely I will be using theta to denote angles. All right. Now let's talk about something called coterminal angles. All right, and the definition for coterminal angles is so we would say two angles are coterminal if when in standard position, if when in standard position, the initial side, the initial and terminal side are the same. All right, and perhaps I should rephrase this better. When their respective, there we go. So two angles are coterminal if, when in standard position, if their respective initial and terminal side are the same. What do we mean by that? Well, let's see. So I'm going to put here two angles in standard position. So let's say that this right here is my first angle. Remember, standard position means you have to start at the x-axis. And there it is. That's the angle that we have there. I'm going to call this, if I measure it this way, I'm going to call it theta. But now, if we were to measure it going this way, and perhaps I'll call that alpha, here, alpha and theta are coterminal angles. They have the same initial side and the same terminal side. So because they have the same initial and terminal side, we would say alpha and theta are coterminal angles. Similarly, we could say something like this. All right, this angle right here, which I'll call alpha, starting from here all the way around there, well, it does start with the same initial side, and it ends at the same terminal side. So overall here we could say alpha, theta, and beta are, oh, hold on. I just realized I called two of these alpha. I have meant to call this one beta. There we go. So now, alpha, theta, and beta are all coterminal angles. Right? They all have the same initial side, and they all have the same terminal side. All right. Now, the next thing we're going to say here is let's talk about radian measure. All right, because remember this lesson's about measurement of angles. So radian measure. All right. So the measure of an angle is determined by the amount of rotation from the initial side to the terminal side. All right. So in general, that's the technical definition of a measurement of the measure of an angle. All right. It is the amount of rotation from the initial side to the terminal side. So let's actually define what a radian measure is for this. So definition of radian. All right. So the keyword here, or the root word that you should be looking at, is there, radii. All right. Essentially, this tells you that this is going to have to do something with the radius. All right. So keep that in mind while we talk about this definition. So 1 radian is the measurement of a central angle theta that intercepts an arc S equaling length to their radius R of a circle. All right. Algebraically, what we're saying is that 1 theta is equal to, let's see, a central angle theta is intercepts an arc S equal in length to the radius R. So in here, if we define it this way, that theta is equal to S over R, here theta measured in radians, right? We could say that when theta is equal to 1, this implies that S is equal to R, all right? We'll use that in a bit. And think about why this would be true, right? If theta over here is equal to 1, then S over R must be the same value, right? Because this whole fraction would be equal to 1. So that's what we're saying here. Now, let's actually give a visual representation of what we're talking about here with these radians. So if I take, let's do this. And so I'm going to take a circle and put it on the X and Y axis. All right. Now in here, let's say I take the following angle. Well, first, notice that this right here, that's our radius, all right? And if I take this angle here, right? So I'm bisecting this arc here and these two, or I'm intercepting this arc here, here, and there. This right here is our angle theta, this measurement. This measurement is also length R. This measurement right here, that is the arc that we're talking about, all right? Now, if in here, if theta is equal to 1, well, then S is equal to R, all right? So in here, that's what we're saying, that like this arc length here, that would be 1 radian based off of this angle here when the radius here and this distance are equal to each other, all right? If we were to look at a whole circle, let me just copy and paste this real quick so I can edit it. If we were to take a whole circle here, and, well, perhaps I'll leave that there. If we were to take this whole circle and split this up in all the ways that this can be split up, in other words, such that we take length R all the way across, all the way around our circle, we would come up with something like this. In here, I'm just gonna put these right here. I'm trying to split this entire thing in equal length distances here. So about there, and about there. So in here, every single one of these arcs, and perhaps I'll move this below. Every single one of these is equal to S. So what I'm saying here is all of these arc lengths are all equal to the radius. So what you would notice there is that it's not a nice perfect number. And then we have this little piece right here, right? It's not a nice perfect number, but how many is it? Well, it's 1, 2, 3, 4, 5. There's 6 of them, and then a little bit of change there. let's talk about what the little bit of change is and how we can actually measure these with numbers, all right? Because right now I've just been talking about this in terms of the actual length of the radius, all right? So if we think about a circle, right, because remember, each of these are arc lengths. If I take the sum of all these arc lengths on this circle, well, I'm just going around the entire circle. So what was that called for an entire circle? Well, normally, if it was just a general shape, we would say that's a perimeter. But for the circle, we're going to call it the circumference, right? So recall that circumference is equal to 2 pi r, all right? Notice how convenient it is that this is already in terms of our radius. So what we're going to say here, well, if the circumference is equal to 2 pi r, then that implies that one full rotation is equal or corresponds to an arc length. This corresponds to an arc length of 2 pi r, right? So maybe I'll say that the arc length there is 2 pi r. The total arc length all the way around the circle, I'm saying, right? Which would tell us that this is approximately, well, 2 pi is approximately 6.28 radians, all right? And let's see how that made sense. Well, we said there were 6 of these, 1, 2, 3, 4, 5, 6. And then that little extra piece right here, that's just 0.28, all right? And it's all because it's defined this way with our pi there. Now, well, what does that imply? Let's see. Well, since one full revolution was equal to 2 pi r, well, actually before that, let me rephrase this. Letting our radius equal 1, we get that the circumference would be equal to 2 pi. So one full rotation would just be 2 pi when our radius is 1. All right, it doesn't really matter that our radius is 1 as far as this next piece, but I want you to get used to thinking about the radius being 1. Now, we were saying that one full revolution would be equal to 2 pi. So that's one full revolution. So in terms of angles, I will draw it here. We're going to say, and I'll do this one in blue, we're going to say that one full revolution is equal to 2 pi. If I said here in yellow, 3/4 of a revolution, well, 3/4 of a revolution, but we can see graphically what that would be already. 3/4 of a revolution, we would stop there. What value would that be? Well, that would be 3/4 of one revolution, right? Remember, of means times. A revolution was 2 pi, so we get here just simply 3 pi over 2. So that would be right here, 3 pi over 2. If we did half of a revolution, well, that would be 1/2 of 2 pi, which just simply would be pi. So that here in purple, half of a revolution would be pi. If I did 1/4 of a revolution, but that would be 1/4 of 2 pi being pi over 2. So 1/4 of a revolution up to here is pi over 2. If I said 1/3 of a revolution, excuse me, 1/6 of a revolution, that would be 1/6 of 2 pi, which would be pi over 3, and that would be approximately here, pi over 3. All right, perhaps I'll do this one still in white, but I'll do it as a dotted line. Well, that's 1/6 of a revolution. We could also say 1/8 of a revolution, which should be 1/8 of 2 pi. So that would be pi over 4. I'm running out of colors here. There it is. So that's going to be 1/8 of a revolution, would be approximately all the way up to here. And that would be pi over 4. And the last one I'll do here would just be 1/12 of a revolution. So it'll be 1/12 of 2 pi, which is pi over 6. Right? And let's see, I've run out of nice colors. Let's do that. So that would be approximately here. That would be this. Oh, look at that, I forgot to do the pi over 4. There we go. All right. So these angles here are going to be very, very common throughout the rest of our studies here with trigonometry. So this was pi over 6. Right? But you could definitely think of these as different kinds of revolutions, or a different fraction of a revolution. Now notice I did all of these with a positive angle because I wanted to talk about all these angles being positive. So in here at pi over 6, that's the first positive angle there that we care about, so on and so forth. Notice also that a full revolution is technically equivalent to saying no revolution, right? So if I'm facing this way, straight to the right, and I do one full revolution, I'm still going to be facing the same direction. So those are technically coterminal angles. All right, now, in here, what I want you to realize here now is that in the first quadrant, we've got all the angles that are between 0 and pi over 2, right? The angle of 0 would be the actually just facing straight out to on the x-axis. Pi over 2 would be facing straight up. But in between here, all of the angles are between 0 and pi over 2. This is where the acute angles exist, right? In fact, by definition, maybe I'll write it down here and then come back to that. By definition, an acute angle is an angle that's between 0 and pi over 2. All the angles that fall into the second quadrant would be between pi over 2 and pi. Those are called obtuse angles. And again, this is when we have them in standard position. So all the angles between pi over 2 and pi are obtuse angles. That's everything that falls in the second quadrant. Now in the third and fourth quadrant, we're not going to have nice names like obtuse or acute, but we will be talking about what angles fall in there. And here, all the angles between pi and 3 pi over 2. And in this last fourth quadrant, all the angles between 3 pi over 2 to 2 pi. Notice I'm not putting or equal to on any of these because the equal to would actually not be in the quadrant itself. That would be on the actual axes themselves. So, all right, let's actually get to some examples. So, let's say, because I mean, that's been a lot of definition. So if I said determine two coterminal angles one positive, and one negative. All right, so let's say that I started with the angle of theta is equal to 9 pi over 4. Actually, yeah, 9 pi over 4. All right, so what I'm going to do here first, I'm going to show you what that angle would look like on the coordinate axis. 9 pi over 4 would be an angle that's more than one full rotation, right? Because remember, a full rotation is 2 pi. So it's actually going to do something like this. It's going to stop there after doing one full rotation. So there's right there in blue, that theta is equal to 9 pi over 4. Now we want two coterminal angles. So we want angles that start at the same spot and end at the same spot, right? We want to have the same initial and terminal side. Well, one thing we can do here is we can remove rotations, all right? So what I can start with here is say that the first coterminal angle, I'm going to take 9 pi over 4 and remove one full rotation. And one full rotation was 2 pi, all right? Now, what we're going to say here is, well, subtract these two. 2 pi is the same thing as saying 8 pi over 4. So 9 pi over 4 minus 8 pi over 4 is just simply pi over 4. And there we go. What we found there is one coterminal angle of pi over 4. Now we've got the first positive response. We need another negative. We need the second answer to be negative. So what we're going to do here is we're going to take pi over 4, or let's do it this way. We're going to take 9 pi over 4 and remove 2 rotations. All right? Removing 2 rotations. And in here, well, what would that do? We have 9 pi over 4 minus 4 pi, but to have a common denominator would be over 4. So what we really have here is 16 pi over 4. And 9 minus 16, well, that would be negative 7 pi over 4. And now negative 7 pi over 4, well, what that would be is we start here. Perhaps I'll do it over here. We start here, and we measure the other way. Right? Remember, when we measure clockwise, it is a negative angle. That's better, I guess. So in here, this angle is negative pi over 4. Excuse me, negative 7 pi over 4. There we go. All right, let's do another one. So essentially, again, it's just about adding or removing rotations. If I had the angle of theta being negative pi over 3, well, let me show you what that looks like. If I put that on the coordinate axis, we have, well, it's going to stop around here. All right, and it would be this right there. That would be negative theta being equal to negative pi over 3. And well, we want to find coterminal angles to this, and to do that, well, we need to either add or remove rotations. If we want a negative, well, we're already starting with a negative value. We want to end up with a positive answer and a negative answer, right? Because we want two coterminal angles. So one of them is going to be, well, we start with negative pi over 3, and we're going to add a rotation. The other one is going to be, you start with negative pi over 3, and we remove a rotation. And remember, one rotation is just 2 pi. So 2 pi in terms of 3 is just 6 pi over 3. So negative pi over 3 plus 6 pi over 3 is 5 pi over 3. Again, this is just 6 pi over 3. So negative pi over 3 minus 6 pi over 3 would be negative 7 pi over 3. Now, what would this look like? Well, let's see. In yellow here, I'm going to do the first one, which is our positive angle. So that angle would be 5 pi over 3, and it's coterminal. The other coterminal angle that we can talk about would be this. that would be negative 7 pi over 3. Right? It is negative because it goes this way. Now, we could have removed another rotation to find another coterminal angle from here, or added another one from here, but we wanted to make sure that we ended up with one positive and one negative. All right, but again, essentially to find coterminal angles, just add or remove rotations. All right. Now, quick definition. Two positive angles are complementary if their sum equals pi over 2. Similarly, two positive angles, I guess I could just copy and paste it. Two positive angles are supplementary if their sum is equal to pi. So what do we mean there? Well, if I put this on the coordinate axis, we're gonna say, well, we're gonna start with, in here, let's say I have this first angle there, and then this second angle here. Remember, pi over 2 was straight up at the top. So what we're saying here is that if I have this angle alpha and this angle beta, we're saying that alpha plus beta is equal to pi over 2, and that would be complementary. Similarly, if I have this first angle here, and then this second angle here, and I call them the same exact thing, beta and alpha, what we're saying here is that if alpha plus beta is equal to pi, because remember all the way here, that measurement was pi, then these are supplementary angles. That's a supplementary. Now, let's figure out how to find some of these. So find the complement and the supplement. Of the following. And I believe we're example C. So let's say theta being pi over 6. Right? So the complement's easy, right? Because we need to just make sure that they add up to pi over 2. So I've been given one angle. I gotta find the other angle. So essentially, what I'm saying here is that pi over 6 plus some other angle is supposed to be pi over 2, which means that that other angle would just be pi over 2 minus pi over 6. At that point, we would say, well, pi over 2 is the same thing as saying 3 pi over 6, which gives us 2 pi over 6, which reduces to pi over 3. So in here, we found that the complement, so this is for complement, the complement of pi over 6 is pi over 3. Now let's figure out the supplement. So using the same idea, like here, I'm going to say that pi over 6 plus some angle is supposed to be equal to pi. So that angle alpha would be just pi minus pi over 6. But pi is the same thing as saying 6 pi over 6. So I end up here with simply just 5 pi over 6. So the supplement of pi over 6 is 5 pi over 6. All right. Now, let's do another example. Let's say that I have 3 pi over 4. All right. So let's find the complement. So by definition, the way that we did it just now was we take our angle and we say that plus some other angle is supposed to be equal to pi over 2. So I get that alpha would be pi over 2 minus 3 pi over 4. But in terms of fourths, pi over 2 is just 2 pi over 4. 2 pi over 4 minus 3 pi over 4 is negative pi over 4. So we found that our complement is negative pi over 4. But that's bad. How come? Let's go back to our definition over here. Two positive angles are complementary. Two positive angles are supplementary. So we're supposed to get positive angles. We just found an angle that, I mean, they did add up to pi over 2 with that original angle that we were given. However, it gave us a negative answer. It's a negative solution there. So this tells us that 3 pi over 4 has no complement. All right, 3 pi over 4 has no complement. But does it have a supplement? The supplementary angle, we would say, well, we need to have 3 pi over 4 plus some angle alpha would have to be equal to just simply pi. So that tells us that alpha would be pi minus 3 pi over 4, which is just 1/4 of pi, right? In here, that would be our supplementary angle. So 3 pi over 4 does have a supplement, because here our answer here, pi over 4, is a positive angle, so we're good, right? By definition, we're fine. So it does have a supplement, but it doesn't have a complement. So essentially, what this tells us is that obtuse angles don't have complementary angles. They only have supplementary angles. Whereas acute angles have both a complement and a supplement. All right. All right. Now, let's talk a little bit about something that you're probably a lot more familiar with. Degree measure. All right. Now, the way that the degree measure is defined is that 1 degree is equal to 1/360th of a revolution. Right, so 1 degree is 1/360th of a revolution, which essentially tells us that 360 degrees is equal to 1 revolution. All right. But what do we know about revolutions? In terms of radians before, we said that 1 full revolution was 2 pi radians. I just read it as rad. 2 pi radians. All right. This also tells us a whole bunch of stuff. It tells us that 180 degrees is equal to pi radians, right? And this implies two very important conversions. It also tells us that 180 degrees over pi is equal to 1 radian, but also that 1 degree is equal to pi over 180 radians. All right. These are our conversion factors. All right. If we want to go from radians to degrees, we use this. So from radians to degrees, this is what we use. If we want to go from degrees to radians, we're going to be using this conversion factor. And what do we mean by conversion factors here? Well, we mean if we want to go and multiply, or if we want to go from one measurement to another, we can multiply by this factor. That's what we call it the conversion factor, because we're going to use this as a factor where this is just equal to 1. All right, and remember, we're always allowed to just multiply any expression by 1. But in here, this 1 happens to be a hidden way of having go from 1 degree to another. Now, let's do some examples. So convert the following. Let's say I have the angle of 135 degrees. Well, if I want to convert that, what I'm saying here is convert it to radians, right? Because I'm starting with degrees, so I want to convert it to radians. So in here, what I'm going to do is I'm going to take 135 degrees and I'm going to multiply it by 1. But that 1, we wanted to cancel out degrees and go to radians. So since we want to go to radians, I need to use pi over 180. So I'm going to multiply this by pi over 180 degrees. Essentially here, you can say that the degrees cancel each other out, so that those units cancel out, and there's always an invisible radians here. So now, 135 over 180, well, they're both divisible by 45. 45 goes into 135 3 times, and 45 goes into 180 4 times. So we end up with here as our final answer is 3 pi over 4. All right, and again, this is in radians. Quick note, if I ever don't specify a unit, it's implied that it's radians. All right, so if there's no unit written, we're talking in radians. With degrees, you have to put a little degree symbol. All right, so essentially if I said something like theta is equal to 10, I'm saying 10 radians. All right, this implies 10 radians. This does not imply 10 degrees. That would be wrong, right? It implies 10 radians. So even if you don't see the letter pi on it, it would still be radians. Anyway, so that was a quick little note. Let's do another example. Let's say that I have theta being equal to pi over 6. All right. So if theta is equal to pi over 6, well, what I want to do is I want to multiply it by a conversion factor, and I want to multiply it by 1, right? Remember, in here, this fraction was just simply equal to 1. So that's exactly what we're going to do here. But since we're going from radians to degrees, I'm going to multiply it by 180 degrees over pi. So I'm going to multiply this by 180 degrees over pi. And recall that this is just equal to 1. At this point, well, we see the pi's cancel each other out. 6 goes into itself once. It goes into 180 30 times. So we end up with just simply 30 degrees. So pi over 6 is the same thing as saying 30 degrees. Let's say that I had theta being equal to negative 330 degrees. Well, we once again start with the same thing. We take the value and we're going to multiply it by 1. But in this case, we want to convert to radians. So we want the radians units on top and the degree units on bottom. We see that the degrees cancel each other out. Both the top and the bottom are divisible by 10. So we'll end up with 33 over 18. But then 33 is divisible by 3 11 times. And 18 is divisible by 3 6 times. So I get my final answer here of negative 11 pi over 6. So negative 330 degrees would just be negative 11 pi over 6. All right. Let's do another one. So let's say that theta is equal to negative 5 pi over 3. Well, I'm going to take negative 5 pi over 3. And since I want to cancel out radians so that I go to degrees, I'm going to put the pi on the bottom and the degrees on top. So at that point we say, well, pi's cancel each other out. 3 goes into itself once, it goes into 180 60 times. So we have 5 times 6 is 30, but we have a negative, and then with that extra 0 there is negative 300, and the units are degrees. So we found that negative 5 pi over 3 is equal to negative 300 degrees. Now, a sector of a circle. So definition. A sector of a circle is the region bounded by 2 radii and the intercepted arc. So 2 radii and the intercepted arc. Right. What does that mean? It means that if I have a circle and I take 2 radii, so let's say, for example, that's a center, that's one radius, that's another radius, right? So this is length r. Similarly, this is length r. This right here is our arc, S. This region here, that is a sector. Right? Now, to find the area of a sector, well, it's the following. So given radius r and central angle theta in radians, we get that the area is equal to 1/2 r squared theta. Right? So let's see how we can go about solving a problem with this. So we're at example I. A sprinkler sprays water over a distance of 40 feet and rotates through 80 degrees, or through an angle of 80 degrees. The question here is, find the area watered by the sprinkler. So let's think about this. All right, if I've got a sprinkler here, right, and this is my fancily drawn sprinkler, and it's rotating over an angle of 80 degrees over a length of 40 feet, well, this right here is a sector. So if I want to figure out the area that's being watered here, well, I've got a formula for that, and it's just A is equal to 1/2 r squared theta. But that was with theta being in radians. So what I need to do is first convert our angle into radians. So in here we're going to say, well, theta is 80 degrees, but we want to multiply it by pi over 180 degrees so that we can change it into radians. This, well, they're both divisible by 10, so it's really 8 over 18, but at that point we say those are both divisible by 2, So it is 4 over 9. So we end up with 4 pi over 9 as our angle, which tells us now that our area is going to be 1/2. Well, hold on, let's try that again. 1/2 times the radius, which was 40 feet, squared times 4 pi over 9. Well, at that point we say, well, 40 squared, that's 1600. And then we have that times 4 pi over 2 times 9, which is 18. Actually, I'll leave it as 2 times 9. You know what? Let's reduce. 2 goes into itself once, it goes into 4 2 times. So really, this 4 over here is just 2. And we still have the over 9. And this is now in square feet, all right? Because of this unit right there. At this point, we say, well, 1600 times 2 is 3200. So we have 3200 pi over 9 square feet. If you plug this into the calculator to figure out exactly what number that gives you, or approximately, we would say this is approximately 1117.01 square feet. All right, but leaving the answer in terms of radians, excuse me, in terms of pi, is what I meant to say, is preferred. All right. All right, so that was the area of a sector. Now, that one wasn't too bad. Let's talk now about arc length. All right, how to find the arc length. Now, if you recall from earlier, we had that theta was equal to arc length over radius. Well, this just simply tells us that the arc length is equal to the radius times the arc length, times the angle, the radius times angle. All right. So, and this has to be in radians, all right, because this was in radians. This was a definition for 1 radian. So that is our arc length. S is equal to r theta, or theta times r. So let's do an example. So that was example I. So we're at example J now. A circle has a radius of 27 inches. Find the length of the arc intercepted by a central angle of 160 degrees. So, all right, so let's see. We've got a circle of radius 27 inches, and we've got an angle of 160 degrees. We want to find the length of the arc intercepted by that. So let's see what we're talking about. So we've got a circle. We've got the radius of the circle. Well, you know what? Let me put this in on the coordinate axis. Good enough. So we've got an angle here of 160 degrees. That would be somewhere around over here. And what we want to find out is the length of this arc. All right, we want to find out that arc length. So, well, we have the formula. We have that S is equal to r theta, or theta times r. But this was in radians, so the first thing we need to do is convert our angle. We had 160 degrees. To convert it to radians, we multiply by pi over 180, right? And then we say, well, let's reduce. 160 is divisible by 10, 180 is divisible by 10. At that point, those are both divisible by 2. 16 divided by 2 is 8. 18 divided by 2 is 9. So we end up simply with 8 pi over 9. And that's in radians now. So our arc length now is going to be the radius, which was 27, times our angle, which was 8 pi over 9. All right. And remember, this was 27 inches.
At
this point, we say, well, 9 goes into itself once, it goes into 27 3 times. 3 times 8 is 24, so we have 24 pi inches. Right? Now, if you were to plug that into the calculator, well, we know that pi is approximately 3.14, so this would be somewhere in the higher 70s, maybe low 80s. But in any case, we would just leave it as that, 24 pi. All right, we prefer the exact answer. So our arc length there, this was 24 pi, where our radius was 27 inches. All right. Now, let's talk about linear and angular speed. All right. So, linear and angular speed. Before I give you the definition, I want to give you the visual as to what we're talking about when we have that. So, let's say that we've got a particle here moving around a circle. All right, so we've got this point moving around the circle. And I'll put this in the coordinate axes just for the sake of making a point. All right, so this is moving around our circle, all right, going this way. Now, there's two things changing here. How fast we're moving along the circle, but also how fast the angle is changing, all right, as we're moving there. So in here, we have, for linear speed, we're essentially saying we've got this arc here. At some other point here, the arc has gone all the way there. How fast did we go from there to there? That is linear speed, all right? Going along this way is linear speed. But if we said how fast did the angle change from here to here, that is angular speed, all right? So I want you to think about that, how fast the angle is changing, all right? Versus how fast are you moving in position. So the definitions are simple. The linear speed, we do it as velocity is equal to arc length over time. All right, and this was arc length over time. Right? That's linear speed. Angular speed, right, which we will define it with omega. This is equal to the central angle over time. All right, so in here this is going to be central angle over time. All right. So again, one is measuring how fast you're moving around the circle. The other one's measure how fast the angle is changing as you're moving around the circle. All right, I think I'm at example. Okay, yeah, it's okay. Let's say we're looking at a clock. All right, so the second hand of a clock is 8 centimeters long. Find, so we're going to say find the linear speed, and that was supposed to say speed. There we go. Of the tip of the second hand as it passes around the clock. All right. So we're looking for the linear speed. All right. So since we're looking for the linear speed, we need the arc length over time. All right. So let's do it this way. We can say that since we're talking about the second hand, all right, and if we look at a clock, we're saying, well, this hand right here is 8 centimeters. And it's moving along all the way around the clock. So essentially, that hand itself just creates its own circle of radius 8. And that was a horrible drawing, but that's okay. Let's fix it. There we go. So in the second hand, that's what this is doing. Now, the question is, how fast is this moving? Well, we know that one revolution would take 1 whole minute. So we would say it's 1 revolution per 1 minute. All right, that's how fast it's moving. Now, what does that mean? Well, let's think of this. Well, we want to figure out the velocity, so we need to do the arc length over time. Okay, so the velocity, which is the arc length over time. Well, what is the arc length? The arc length, we said, is 1 entire revolution over 1 minute. If we do this as the minutes, if we're going to do it per second, we're going to say this would be for every 60 seconds. Well, revolution, let's see what we can do here for the arc length. We know that the arc length is equal to theta times r. So what is the angle that we're going over? We're doing a whole revolution, which is 2 pi times the radius, which is 8 centimeters. So we have essentially 16 pi centimeters as the entire arc length. Reducing this, we would say, well, 16 is divisible by 8. 16 is divisible by 4, giving us 4 pi, and 60 is divisible by 4, giving us 15 pi. So we have 4 pi over 15 centimeters per second. That's how fast this is moving along the clock. All right. In terms of what this is approximately, if you plug this into the calculator, it's approximately 0.838 centimeters per second. So as this is moving each second, it's being almost 1 full centimeter. Now, let's do another example. So that was example K. Example L. Let's say that the circular blade of a saw rotates at 2400 revolutions per minute. All right. The first question I'm going to ask here is find the angular speed of the blade. In radians per minute. And the second question here is going to be, if the blade has radius 4 inches, find the linear speed of a blade tip. All right, so let's go through this problem. So we have a circular blade of a saw that rotates at 2400 revolutions per minute. So what is that saying? That's saying that we have essentially this circular saw, and I'll make it look like a saw by putting all these awesomely drawn, this is going to take too long, all these awesomely drawn blades. Look at that. What I do for the sake of accuracy. All right, so in here we've got this blade spinning, right? And we know it spins at 2400 revolutions per minute. All right, we want this in radians per minute. All right, well, let's do this. 2400 revolutions. So this is the solution to part 1. 2400 revolutions per 1 minute. We want this in radians. So what we're going to do here is, well, one revolution, we know one revolution is equal to 2 pi radians. So all we need to do here is convert 2400 revolutions into radians. So we're going to say this is 2400 times each revolution represents 2 pi radians. We have this for each minute. We wanted it to be per minute. So this is going to give us 4800 pi radians per minute. So that's the angular speed, all right? That was our angular speed. And perhaps I should have started with our formula because the angular speed was theta over time, the angle over time, all right? That's how we got this. All right, so that's part one. Part two, if the blade of the radius has 4 inches, find the linear speed of a blade tip. All right, so now we're seeing, so again, in here, this just tells us how the angle is changing. Now what we're looking at is how fast the tip is moving along this. All right. So, well, we know that the velocity is equal to the arc length over time for linear speed. The arc length was r theta, and we have that over time. We're going to keep time simply as 1 minute. But we have, well, the radius was, what was it? It was 4 inches. So we've got 4 inches times the angle. The angle we found over here, right? We converted these 2400 revolutions into radians by saying, well, one revolution was 2 pi. So we got 4800. So in there we have 4800 pi. All right. And at that point we say, well, 4 times 4800, it would be 19,200 pi, and this is in inches per minute. All right. And by the way, if I had said that we wanted this per second, I would have needed to rewrite here. Maybe I'll do that in blue here. So for these, if I said in radians per second, well, this would have to be 4800 pi radians over 60 seconds, right? Because 1 minute is 60 seconds, and then reduce, which would give us, well, these zeros cancel out. 6 goes into 48 8 times, so I would have 80 pi radians per second. Similarly over here, it only changes at the end here. The 1 minute needs to be changed into 60 seconds. And we have 19,200 pi inches for every 60 seconds. Reduce, 6 goes into itself. That's me. 10 goes into 60 6 times. 10 goes into 19,200, 1,920 times. And then we see, well, those are both even numbers. 6 is divisible by 2, becomes a 3. 1,920 divided by 2 is going to be, what is that? 9,600. Is that true? 9,000 plus 9,000 is 18,000. This is me. We're not doing thousands, we should be doing hundreds. There we go. That makes way more sense. So let's recap that. So I was dividing 1,920 by 2. So we can check this right, because 900 plus 900 is 1800, and then 60 plus 60 is 120, and then 1800 plus 120 would be that 1920. So we know we're correct there. But that's still reducible. Let me just write down what we have so far. We have 960 pi over 3, and we have it in inches per second. But 3 goes into itself once, and 2 goes into 960, 320 times. So what we have here, 320 pi inches per second. All right, so that's if we wanted things per second. All right, so in there, that is the end of 4.1. All right, but again, at the very end here, I want you to keep in mind that With linear speed, we're talking about how fast it's going around the circle. With angular speed is how fast is the angle changing around the circle. All right. All right. So that's the end of 4.1.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.